Okay, so good morning, everyone. My name is George Constantinis. I'm a professor at Imperial College London, and I'll be chairing session 1 today. The first speaker in session 1 will be Linus Wong from the University of Pennsylvania. Linus is currently an electrical and systems engineering PhD student at the University of Pennsylvania, advised by Professor Jing. His research interests include high-level synthesis, memory interface, and near storage computing. Previously, he obtained his MPhil in electronic and computer engineering at the Hong Kong University of Science and Technology under Professor Zhang. He graduated from the Chinese University of Hong Kong with BEng in computer engineering in 2019. Over to you, Linus.
Can you see this one? Okay. Thanks, George, for the introduction. Start. My name is Linus, and I'm a PhD student from. I'm a PhD student from University of Pennsylvania. Today, I'm going to introduce our work on DONGLE, direct FPGA orchestrated NVMe storage for HLS. This work is done in collaboration with my colleague Jialiang Zhang under the guidance of Professor Jing. First, let me give a quick overview of DONGLE. DONGLE is a unified interface for HLS storage and memory. It enables clean single-source HLS programming and also a portable unified code to target multiple memory and storage devices. Performance-wise, it's efficient with a direct control and data path connecting between FPGA and SSD, bypassing the CPU for high bandwidth, low latency access. The remaining of my talk will be organized as follows. Motivating our work is HLS plus SSD as a simple, performance, and scalable solution for terabyte scale applications. However, the current multi-source and entangled HLS storage programming is difficult, and the indirect control path has a high latency overhead. To overcome these challenges, we propose DONGLE. DONGLE enables single-source decoupled HLS storage programming with a direct control path for clean design, portable code, and high performance. Our experimental evaluation shows that DONGLE can achieve 2.4 times code reduction and speed up application by 2.3 times, demonstrating programmability and performance improvements. Next, I will go over the motivation of our work. Motivating our work are the two ingredients for terabyte scale acceleration. High-level synthesis, or HLS, provides a simple and efficient means to describe hardware acceleration. It's easy to use and has extensive vendor and community support. As a result, it has been widely adopted for a variety of applications. On the other hand, solid-state drive, or SSDs, can store terabyte-scale data on a single device. Compared to previous storage technologies, SSD provides a high bandwidth, low latency access to data, making it ideal for data-intensive applications. If we combine both HLS and SSD together, we get a simple, performance, and scalable solution for terabyte-scale applications. For example, database, graph processing, machine learning, and so on. However, currently there's a large interface gap between HLS and SSD that prevents us from combining both together. On one hand, we have HLS, which addresses memory in byte addressing and access data through direct load store. On the other hand, we have SSD, which presents data as a collection of blocks. Addressing and data transfer are done in granularity of blocks, which are hundreds to thousands of bytes. Moreover, for SSD, we cannot directly access the data. Instead, we need to prepare an intermediate buffer, which is a small memory region, and copy the data over to the buffer before accessing the data. This large interface gap between HLS and SSD prevents us from combining together for our terabyte scale acceleration. The current HLS plus SSD programming strategy is to program them using PCIe peer-to-peer, also known as P2P. The latest FPGAs and NVMe SSDs supports a direct P2P data path between them, bypassing the CPU host memory for high bandwidth data access. However, because of the previously mentioned interface difference, the HLS kernel cannot directly talk with the SSD controller. Instead, the HLS kernel needs to first talk with the CPU host, asking the CPU host to issue the storage request on the HLS behalf. Moreover, users need to write their own host code to orchestrate between FPGA and SSD. All of these combined results in a long and indirect control path from HLS to CPU to SSD, which leads to programming and performance challenges. From a programming perspective, HLS plus SSD requires a multi-source programming due to relying on hosts to orchestrate the storage control. Moreover, because users are responsible for writing both the algorithm and storage control code, resulting in entangled algorithm and storage control. These two combined makes programming HLS storage access in current programming environments tedious and error-prone. Performance-wise, the indirect control path also introduces a high control latency overhead that can exceed the combined computation and data transfer time, making it the main bottleneck in HLS storage applications. Next, I will go over these challenges one by one. Before talking about HLS storage access, let me briefly recap how we access memory in HLS. Variables in FPGA DRAM are directly accessible in HLS. This enables us to write our code all in HLS code for a single source programming. Moreover, the byte addressing and load store abstraction enables users to focus on writing their own algorithm for a clean algorithm specification. However, FPGA DRAM are generally smaller than terabytes, which limits us from using it for terabyte scale applications, which exactly is what motivates us to use storage. Storage provides plenty of capacity larger than FPGA DRAM. However, unlike DRAM, the variables in storage are not directly accessible or addressable in SSD. Instead, we need to introduce separate buffers in the FPGA DRAM and partition the address space into two parts. First, we address at block level using block 1, 2, 3 variables. Then we address at byte levels using the index 1, 2, 3. This results in a manual partitioning of the address space. Moreover, because HLS cannot directly talk to the SSD, we need the host to orchestrate at the block level and the HLS to process data at byte level. Whenever HLS wants to address new data, we need to copy over the data from SSD to FPGA DRAM before we can process it. This also results in a multi-source programming requiring partition of algorithm. Next, we are going to talk about how this also results in an entangled storage and algorithm. Because HLS needs to suspend execution and synchronize with the host to communicate the storage access request, we need to add suspend resume logic in the HLS to synchronize with the host. Furthermore, we also need interfacing code to communicate which storage address we wish to access. Finally, to make the actual request, we need to add storage control code on the host side. All of this results in an entangled algorithm and storage control code that makes the already tedious multi-source programming even more error-prone. Next, let's talk about the performance implication of this indirect control. As we have discussed before, HLS kernel need to first suspend execution, synchronize with the host, and communicates the storage access address. The host then relays this information to the SSD controller, which copies over the data to the FPGA DRAM through direct P2P data path. The SSD controller then replies to the host, and the host can resume the execution of the HLS kernel. All of this results in 4 control transactions and 1 data copy, resulting in a total of 5 PCI transactions, even using P2P, which means that there's a complicated control path and a high latency. To show this control latency overhead is significant, we profile 6 different storage applications and break down the computation time between FPGA computes, SSD data transfer, and the control path latency overhead. We find that FPGA computes only contribute to 10% of the overall runtime. On the other hand, the SSD data transfer contribute to 38%. The remaining 52% are all the control path latency overhead, which exceeds the combined runtime of both the FPGA computes and SSD data transfer, making it the main bottleneck of these HLS storage applications. To address the programming and performance challenges, we have 4 design goals for DONGLE. First, for programmability, DONGLE enables a single source programming for a simple design, simulation, and debug of storage applications. Moreover, DONGLE decouples the storage control from algorithm to allow users to cleanly specify algorithms. From a programming performance perspective, DONGLE eliminates the excessive control path for a low latency storage access. Finally, DONGLE is also backward compatible with existing HLS code targeting DRAM and use a design flow that is non-intrusive to minimize changes to users' program and experience. First, I'm going to talk about the programmability of DONGLE. To enable single source programming, we first identify that the indirect control path is the cause of the need for multi-source programming. That's why DONGLE eliminates the need to as the CPU host as the middleman and connects directly between HLS kernel and SSD controller. This direct control path eliminates the need for suspend resume code and host HLS interfacing code, resulting in a single source programming. However, despite the single source programming, our HLS code still comprises of entangled algorithm and storage control. This is because we still need to work with the block level abstraction of the SSD. To tackle these challenges, we designed a storage control architecture that handles the storage details of SSD, exposing a byte addressable and low storable address space of the SSD. This enables users to write HLS code composing an entirely algorithm, leaving the storage control detail to DONGLE for a decoupled algorithm and storage control. Next, I'm going to talk about the performance aspects of DONGLE. As I have discussed before, the complicated and indirect control path is the cause for the long control path latency. That's why in DONGLE, we eliminate the need for CPU hosts and connect directly between HLS kernel to the SSD controller through the DONGLE module. Instead of communicating to the host for storage access, with DONGLE, the HLS kernel directly talks to the SSD controller through the DONGLE module. The SSD controller then returns the data to the HLS kernel and responds through the DONGLE module. All of this results in 3 PCIe transactions, which is a reduction from 5 for P2P, and have a simple control path for low latency storage access. Finally, let me talk about how DONGLE enables backward compatible code with existing HLS code targeting DRAM and the design flow. DONGLE introduces a unified storage and memory programming. Users write a single unified HLS code to target both storage and memory, and this code is also backward compatible with existing HLS code targeting DRAM. To specify which storage and memory to use, users write link directives. For example, we highlight in blue here to show that we wish to bind the kernel interface to storage. This results in a storage design. Alternatively, we can also choose to bind the kernel interfaces highlighted in green to DRAM, which results in a memory design. Finally, we can choose to bind different kernel interfaces to different memory and storage devices, resulting in a combined storage and memory design. Here, we can see that all 3 of these designs are generated from a single unified HLS code and differs only a few lines in the link directives for unified programming. Now, let's talk about the design flow of DONGLE. As we have discussed before, users write their HLS code to describe the computation algorithm and use the link directives to control the overall architecture. The HLS code is then synthesized with the HLS compiler to obtain the synthesized HLS kernel. The HLS kernel, together with the link directives, is used by the dongle linker to generate the overall FPGA block design. The block design is then implemented using a FPGA toolchain to generate the final bit stream used to reconfigure the FPGA at runtime. If we compare the flow of dongle on the left and the workflow of existing HLS environments on the right, we'll see that they are very similar in both user inputs and workflow, presenting a familiar experience to users. Finally, to evaluate dongle, we use off-the-shelf FPGA and SSDs and choose 6 different workloads spanning across sequential and random workloads, as well as database, linear algebra, and machine learning. For comparison, we evaluate dongle against a PCIe-based P2P baseline and represent programmability using lines of code and performance using application throughput. First, let's take a look at the programmability results. The lines of code for the P2P baseline are shown in the green bar, while the lines of code for the dongle are shown in the blue bar. We can see that across 6 different applications, dongle significantly reduced the lines of code for an average of 2.4 times. For comparison, we also include the lines of code required for existing designs targeting DRAM in the red bar. If we compare the red bar with the blue bar, we find that they are very similar, which because dongle enables a unified programming across storage and memory and is backward compatible with existing HLS code. Next, we present the performance results. Here, we present the performance numbers normalized to the SSD specification. We see that dongle achieves near 100% performance of the SSD, indicating SSD saturation. Moreover, when compared to the P2P baseline, dongle also achieves an average of 2.3 times speed up, thanks to eliminating the control path latency overhead. To conclude, our work is motivated by HLS plus SSD as a simple, performance, and scalable solution for terabyte scale applications. However, the current multi-source and entangled HLS storage programming is difficult, and the indirect control path has a high latency overhead. To overcome these challenges, we introduced dongle, which enables single-source decoupled HLS storage programming with a direct control path for clean design, portable code, and high performance. Our experimental results shows that dongle can reduce lines of code by 2.4 times and speed up applications by 2.3 times. Thank you. I'm now happy to take questions.
Well, maybe I can start.
So have you considered another potential baseline where your host load the data from SSD into host memory and then coordinate between the host and FPGA memory?
Yes, so when we choose the baseline, we decide to choose P2P programming because there are extensive literature that compared P2P programming with loading it through the host memory through a ping pong buffer, then loading it to the FPGA memory. This work shows that P2P performance are higher because there's a one less additional copy through the host ping pong memory. That's why we choose to use the P2P as our baseline.
Hi, nice talk. Have you considered the security and access privilege aspect of it now that you're not going to the host? Let's say you have one application which is not supposed to have access to all the data in the SSD. How do you create the demarcation? Or if you load a subsequent application on the FPGA, how do you make sure it doesn't have access to the previous application?
Sorry, can you repeat again? I couldn't hear.
Yeah, my question was, how do you ensure the access privileges of the file in the SSD are maintained? Have you looked at that aspect?
security. Okay, so currently, our storage accessed through dongle acts very similarly through like a FPGA memory. This means that we use existing OpenCL calls to access the storage on FPGA. So our security policy will be similar to existing security policy on FPGA memory.
Okay.
Okay, then I think in the interest of time, let's close this one. Thank you.